angle alpha to the magnetic flux of the field. So now this, we are considering a particular conductor here, okay, a conductor, and the conductor we are going to draw, right? Let us say this is straight conductor. So you have this. You have this one is the length of the conductor. Okay, that length of the conductor. Then you have from this side. All right. Then now, according to there's what you call Fleming's rule as well. All right. I've mentioned 3 rules that you are going to place a study on. You are going to study corkscrew rule in magnet, clench rule, and you are going to study Fleming's left hand and right hand rule. Okay. So now this is n electrons. N electrons. All right. Then you have F. That is the force on the magnet, and you have the magnetic field intensity, F and B, and B here, the magnetic field intensity, and what you call the magnetic field strength. So that's the conductor we are going to consider. So if you use the Fleming's rule, now from that, if this is a conductor, from the diagram above, with the electrons in the rod move from one end, all right, there's an electron moving from one end of the conductor to the other. What is going to happen? If it's moving from one end of the metal rod to the other end of the metal rod, then it's going to move a distance n. Then the velocity, all right, will be given by v is equal to distance over time. That's what's going to happen, all right. The velocity of the electron, if there's an electron moving, all right, from one end of the metal or the metal conductor to the other, because this is n electron, which is number of electrons, then we are going to be having what? Your velocity is equal to the distance covered by the electron, all right, to the time taken. So we can use down as equation 1. Okay, so if that's the velocity, all right, which is v is equal to L over t, then what is going to be the value of t? If you make time taking of the electron set of formula, from v is equal to L over t, all right, we have what? Vt is equal to what? Is equal to L. Then we have L, all right, t now is equal to what? L over what? L over v. So that is the value of t in that place. All right. What I just did was to make this sort of formula from Vt is equal to L and divided both sides by V. This cancels the then T is equal to L over V. So that is the value of time taken, all right, in the electron. So if you move further on that, now our charge, all right, is Ne. As the current passes through the rod, if n number of electrons are made to pass out and replaced by another n electrons, all right, the total charge flowing through it is Q is equal to Na. So your total charge Q is equal to number of electrons multiplied by the electronic charge. That's what is going to be total charge if the electron is passing through the rod. So that one will give us equation 2. So we can use equation 3. Let us see this one is equation 2. Then we have equation 3 here, or equation 1 and equation 2. Anyway, you want to arrange it. Then from that end now, our time taken for the electron is the length over velocity. Velocity is equal to length over time. Then the charge in the electron is number of electrons multiplied by the electronic charge, which is an equivalence of 1.6 times 10 raised to the power minus 19 coulomb or joule. So now, if you move on, the rate of flow of charge, all right, which is the current I, is given by what? So let us find current. Once we have been able to calculate for or find the value of charge there, what is now going to be the value of the current? So now we said that our Q is equal to Ne, all right, and of course we know that our Q is equal to IT, because at the end, what we are going to be having as the value of I is to be Ne over T. Okay, so we have Q is equal to IT, and we are looking for current. What's going to happen? That is Q is equal to, now this Q is equal to IT. So we are looking for current, IT then divided by T and divided by T. Okay, this one has gone. Then we'll have Q over T is equal to I, or I is equal to Q over T. But our value of Q, which is the charge, is now what? N number of electrons multiplied by A. Then we'll have I is equal to Na over T. So this is how to prove a magnetic force. So if I is equal to Ne over time taking, all right, then let us impute the value of T at that side, because we have the value of T already. What is the value of T? The value of T gave us an equivalent to us. We can say where T is equal to L over V. If T is equal to L over V, then I now have I is equal to Na over NYCT. I'm going to be writing L over V. then I have I is equal to, I think, NEV over L. Right, that's going to be my next value of what? Of current. Now we can either use current is equal to charge over time, or Ne, which is number of electron, all right, multiplied by electronic charge over time taken, or we can use current is equal to the number of electron, all right, the electronic charge, then the velocity over length. So we can use Q over T, we can use Ne over L in magnet, we can use I is equal to NeV over L. So if that has been gotten rightly, then we can move on. So that NeV over T can now give us, so if you use one as equation 1 and use equation 2, you can use one as equation 3. Alright, and if you substitute an equation for T, you can, that one will now be equation 4. So now if you move on, when a charge moves in the magnetic field, it experiences a magnetic force, of course, whose values, alright, when a charge moves in the magnetic field, it experiences magnetic force whose values and direction are given by the equation below. So now your magnetic force is supposed to be given two values, alright. You can either have it from BIL or you can have it from BQV. Now let us have our values of magnetic field here. So if you have BIL sine alpha, which is a value that we are conversant with for a magnetic force, F is equal to BIL sine alpha. So if F is equal to BIL sine alpha, all right, now we are going to be imputing the value of I. Now, meanwhile, for that BIL sine alpha, this is if the wire is at right angle to the fluid. If it's not at right angle to the fluid, all right, or it's not subtend at any particular angle, just use BI. So F is going to be what? BIL alone. If there's no angle subtended, but if there's an angle subtended, you have F is equal to BI sine theta or BIL sine alpha. So your B is the magnetic field, your B is force, magnetic is then I is the current, L is the length of the conductor, then theta or alpha in the context is the what? Angle subtended. Now, meanwhile, now there are two different ways your angle can be subtended. It's either it is parallel, all right, your conductor is parallel, or your conductor is what? Is at right angle. So your conductor can be like this. If your conductor is like this, all right, your conductor is parallel to the field, and if your conductor is perpendicular to the field, and if your conductor is straight, we can say it is what? It is parallel to the field, something of this nature. So you are having a straight conductor, so something of this, we can say it is what? It is parallel to the field. So these are the two different ways you can have your what? Your angle subtended. Angle can either be subtended perpendicular to the field, or what? Parallel to the field. So if it's at right angle to the field, what is going to happen? So this is the value of alpha, all right, and this is another value of alpha. If it's at right angle to the field, you have what? Alpha or theta, or we can say theta or alpha is equal to 90 degrees, all right. But if it's parallel, all right, theta or alpha is equal to 0 degree. Are we together? So now if I give you a question and I said that it is parallel to the field, just use the value of what? Of theta to be 0 degree. But if I say it's perpendicular, just use the value of what? Theta to be what? 90 degree. So you can have it in two different manners. So if that's the case, that's what I'm going to. I want to use that F is equal to BI sine alpha as the magnetic force, or BI sine theta, to prove an equation. So what is the value of I that we have? Our value of I is now given to be what? To be NeV, all right, over L. So if I want to impute it, all right, you can draw this diagram down for parallel and perpendicular angles suspended in the field, and while our F is equal to BI sine alpha is the value of the force. So if that is the case, now I'm going to be having my sorry. So I'm going to be having the value of of I imputed in that place, all right, which now gives me a value of I to be I is equal to, I have NeV over L. So I now have F is equal to, so anywhere I see I, I'm going to be writing B. The value of I now is not going to be NeV over the length. Then I have another length here because this is the value of I. Then I have L here, then this sine what? Sine alpha. Then F is equal to, so L has gone with 1 L. This B into NeV, right, over L. Then L cancel L here. This is sine alpha. Then I have F is equal to, what is left? That is what? BNeV, alright, sine what? Sine alpha. Okay, so if F is equal to BNeV, my E is equal to Q. Alright, we have been doing that. E is equal to Q. So if E is equal to Q here, then I can also have what F is equal to what B. All right, this N is number of electron is 1, so B multiplied by 1 multiplied by anywhere you see E, write Q, then sine what? Sine alpha. Then at the end, we are going to be having what? F is equal to what? BQV. All right, sine what? Sine alpha. Now, if there is no angle subtended, it's going to be what? F is equal to what? BQV alone. All right, so that is what we are going to be having as the second value of the magnetic force. So, in that term, we can say that the two formula for magnetic forces are F is equal to BIL sine what? Sine alpha, or F is equal to what? BQV. All right, sine what? Sine alpha. If there is no angle, if the angle subtended, all right, is parallel, theta is equal to what? 0 degree. If it's perpendicular, theta is equal to what? 90 degree automatically. Then if there is no angle subtended, we can just use F is equal to BIL or BQV, or what? F is equal to what? BIL. These are the two values we are going to be having. Okay? So that is that for that. Alright, so let's take question, alright, and see what is going to happen for how to calculate for the force in a magnet. So calculate the magnetic force experienced by an electron moving with a speed of 500 meters per second. So in that question, all right, a speed of 500 meters per second, they say to calculate for the force when the speed is what? 500. So force is unknown, then speed is equal to 500 meter per second. So you note it down. Okay, so when it enters into a magnetic field of strength 0.2 Tesla, so the magnetic field intensity or strength in that place is 0.2 Tesla. All right, then if you move on, what the next thing? 0.2 Tesla at an angle 30 degree to the field. So they give an angle, so there's an angle subtended 30 degree. If they will have said that the angle is parallel to the field, automatically theta is equal to 0. If they will have said it's perpendicular to the field, the theta is equal to 90 degree. All right, but here theta is equal to 30 degree as given in the question. Okay, quite important. All right. So the next thing, to the field lines and the dimension of the magnetic field. So we have to calculate for the what? Force and the dimension of the field. So which of the value can we use in that place? Don't forget that your length was not given, but magnetic field intensity velocity was given in the question. So, and of course, electronic charge is a constant, 1.6 times 10 raised to the power minus 19. Okay, so if that is the case, what's going to happen is that I'm going to be having my F is equal to what? BQV sine what? Sine alpha. If they will have given a value of I and L, all right, I will have just used F is equal to BIL sine theta, but because it was not given, that is the value I'm going to be applying. F is equal to BQV sine alpha. So if that is the case, to calculate on my force, I have F. What is the value of B? Value of B 0.2. What is the value of Q? Value of Q is 1.6 times 10 raised to the power minus 19. Then what is the value of V? V was given to be 500, so you multiply 0.2 multiplied by 1.6 times 10 raised to the power minus 19 multiplied by the velocity, which is 500. Then sine the alpha there was given to be, which is theta, is going to be 30 degree. Sine 30 is 0.5, of course. So when you calculate everything together at the end of the day, you are going to be having a particular value for what? For your force. All right. So you have F is equal to, there's no need for conversion because everything is on the unit, right unit. Q is 1.6 times 10 raised to the power electronic charge minus 19. Velocity is 500. Then multiplied by sine alpha. Sine alpha is sine 30 degrees. So at the end, we are going to be having a value altogether to be multiply all of this. So that is F is equal to 0.2 multiplied by 1.6 times 10 raised to the power minus 19 multiplied by 500 multiplied by sine 30 is 0.5. Then if you multiply everything together, you are going to be having 8 point something, right? I think 8.0 times 10 raised to the power 17, thereabout. Okay, so you have, 8.0 multiplied by 10 raised to the power 17. 8.0 times 10 raised to the power 17 Newton. Alright, that's what you're going to be having at the end of the day if you calculate for that magnetic. So that is how to attempt questions. Alright, so you can also try these ones in your in your individual exercise. So a wire carrying a current of 5 ampere, alright, and 2 meter. So they gave current, alright, and they gave length 2 meter. In length is placed in a field of flux density 0.3 Tesla. So B was given, all right, to 0.3 Tesla. So what is the force on the wire if it is placed? What is the force on the wire if it is placed at right angles to the field? Of course, I've said already that if it's at right angle to the field, that question, the parameter in the question suggests that the magnetic force we are going to be applying is F is equal to BIS sin theta. So if that is the case, we are going to be equating the value of alpha of theta to be 90 degrees because it is perpendicular to the field. All right. Then they said at 35 degrees to the field, that one is straight away. Just use theta of alpha to be 35 degrees. Then along the field means it is parallel. That is alpha or theta is or alpha is equal to what? 0 degree. Right. So that's basically how to calculate for your magnetic force. All right. If it's parallel, F is equal to what? BIL sin what? 0. If it's perpendicular, F is equal to what? BIL sin perpendicular sin 90 degree. That is in terms of that parameter. But in terms of second parameter, this one you're having in terms of magnetic intensity or strength, magnetic strength, current, and what length. But if in terms of the magnetic intensity, the charge and the velocity, so you have BQV. All right. If it's parallel, that is sin what? Sin 0 degree. And if it's perpendicular, you have what? BQV sin what? Sin 90 degree. This parallel. Okay, why this one is what? Perpendicular, this parallel, and this perpendicular. So that's how to go about all of those concepts. Quite important. So all right, do more exercise on that. When we meet in the next video, I'm going to continue, all right, the second part of the topic. All right, and thanks for watching, and God bless you. All right, we'll see you again in the next video.